but it's
like 11 strong.
Okay, let's wait.
Give like a couple of minutes.
Oh yeah, sure.
Okay.
Right. Maybe. I know that you're trying to be super punctual, but
okay.
Maybe 2-3 minutes. Bullshit. Bullshit. I think it is a result.
Maybe 1 more minute. 1 more minute, I guess.
Yeah. Yeah, you should probably read the rest, but that you could see. Yeah, Gregor that I was not work. Which I mean, I honestly what it means, but it sounds good. But anyway, I think at least.
Hello, everyone. It's my honor to introduce our speaker, Ayush Jaiswal. He's a PhD student at the Center for Vision, Image, Speech, and Text Analytics of USC ISI. And he works on various aspects of representation learning and adversarial learning and verification of semantic integrity in multimedia data. So he's going to present a unified invariance framework for supervised neural network. Thank you.
Hi, everyone. I'm Ayush, and I will present our work on unified adversarial invariance at the USC ISI VISTA Center. I will first introduce the concept of factors and what constitutes as undesired factors, what invariance is and why it is needed. Then I will describe our new general framework for invariance through split representation learning. I will describe our implementation of the framework, which is adversarial. And finally, I will provide empirical results and conclude the talk. So starting off, supervised learning involves mapping data to targets Y. And this usually involves learning a function of the data in terms of a parametric model, and we want to estimate the parameters of this parametric model from the data. And training usually involves optimizing a loss function, which tries to bring the predicted Y close to the real Y. And this is done through learning to associate different factors of variation of data with the target. For example, if we want to predict whether this image is of a dog or a wolf, we would look at different proportions of the body of the animal, like what is the length of the legs, what is the size, what is the height, how long is the mouth, stuff like that. But the problem is that data often contains nuisance factors, which are truly irrelevant for the prediction target. That is, there is no correlation between these nuisance factors and the target, but the model might learn some false associations because of the nature of the training process. For example, certain elements of handwriting style might be captured in OCR for identifying what character it is. And lighting conditions might be associated to subject ID when they should not be. And models that learn to falsely associate these kinds of nuisance factors with the target lead to incorrect predictions and often poor generalization, especially when at test time we see data with unseen variations of these nuisance factors. For example, if the wolf versus dog classifier learned associations between the class and elements of the background, that is, whether there is snow or not, it could predict this animal as a wolf instead of a dog. And in fact, this is from a couple of years ago, and this actually happened. So, like, what do we do about this? So, not just nuisance factors, data often contains a lot of biasing factors. So these are a subset of nuisance factors, which should ideally not be related to the target, but the training data contains false correlations between these biasing factors and the targets. For example, gender and race are the top biasing factors in socioeconomic tasks. And without any additional supervision, models naturally associate.
So why do you say they're not well represented in training data? I mean, gender, race will always be represented in training data if it's about people.
Right. By that I meant that there's a skewed distribution. So one gender might be underrepresented versus the other, and that can lead to false correlations in the data. And often a lot of other factors of data are also correlated with gender. So even if you don't account for gender explicit, like if you don't think about gender explicitly, these other factors might be correlated with gender. So naturally, models associate these biasing factors with target because there is nothing telling them that this is a biasing target and not something useful for the prediction task. And this leads to unfair predictions. So to give you an example, again, with the same classification task, what if the training data only showed wolves in snow backgrounds? The model has no supervision. It only sees wolves in snowy background. So it will learn to associate wolves with the snowy background. But this has more serious implications. For example, these are predictions from a real life software that is used for assessing risk factors of prisoners about how likely they are to commit crimes again. And you can see from the example that the predictions are truly biased. So there are two key takeaways. Invariance is required to both nuisance factors and biasing factors, whether they are correlated with the target or not. And what this means is we want classifiers to not associate nuisance and biasing factors of data with the prediction target. A model that does not do this kind of misassociation is called invariant with respect to that factor. There are several methods that aim to achieve this kind of invariant predictions. For example, convolution and recurrence capture different kinds of features. For example, convolution captures features that are invariant to the location of objects, and recurrence captures features that are more reflective of trends in the sequence rather than instance level features. And this makes them inherently invariant. But this is a very inflexible approach. Now we have to come up with design techniques for every kind of possible factor. And this does not scale. So recently there has been a push to new kinds of training strategies that force models to be invariant because of the way that they are trained. For example, a very common technique is data augmentation. So in case of digit recognition, for example, MNIST, you could rotate the digit at various angles and just train a neural network with different rotations of the digit, and you hope that the model will associate all of these different rotations with the digit class. But there is a problem with this approach. This relies on the fact that the model would associate these different variations of the nuisance factor with the target. So what if at test time you see a different variation of the nuisance factor? The model will still make false predictions. So more recently, there has been a push for forcing neural networks to become invariant to factors by exclusion rather than by inclusion. So the model should not even consider these factors in the training process. One way is to use supervised adversaries. So given that a neural network actually learns a latent representation of data, you could force the neural network to not encode certain factors of variation by using an adversarial learning strategy. Second is an information bottle. Sorry.
But if there's other correlated factors that are correlated with these nuisance factors, then you're not excluding those, right?
So if we are doing this in the latent space, then especially if you're doing it using adversaries, then the adversary takes this entire latent embedding and tries to predict the nuisance factor or the biasing factor from it. So it doesn't matter if there are many factors in the raw data that are correlated with the bias or nuisance, the latent embedding will become invariant. The second approach is information bottleneck. So this is used for nuisance cases and not bias cases. And the idea is that if we try to learn a minimal representation of data that is sufficient for predicting the target, we compress away nuisance factors.
Let me try to understand what you mean. So I would assume biases are a subset of nuisance factors. So what do you mean by compress away nuisance factors, but not necessarily biases?
Right. Sorry for the confusion. Here I meant to say that nuisance factors are the ones that are not correlated with the target in the training data, whereas biases are. So ideally speaking, biases are a subset of nuisance, but with respect to training data, they have a different meaning. So in this presentation, I will use the terminology. Whenever I say nuisance, it means a factor that is not truly correlated with the target in the training data, whereas a bias is.
And just so I understand what you mean, the nuisance factor in the previous example, the image was like no.
That would be a bias.
Or would that be a bias effect?
Yeah. So if the training data had both dogs and wolves in snowy backgrounds and the model still learns it, then it's a nuisance factor. But if the training data only has wolves in snowy backgrounds, there's a bias. Now the snow background is correlated with the target.
All right, yeah. Thank you.
Yeah. Sorry for the confusion.
No.
So given this setup, I will now present our method for learning invariance to both nuisance and biasing factors of data. So let's start with trying to understand what factors of data mean. So in a completely abstract way, we can say that data can be represented as a set of atomic factors. So these are indivisible factors. And if this is the case, then you can always create a partition of this set where one portion of it, Fy, is required for predicting Y, and Fy complement is not required for predicting Y. This is nuisance, that is the factors that are not correlated with the prediction target. And in this setup, estimating the probability of the posterior probability of Y given X as a probability of Y given Fy is preferred over the probability of Y given X, because now when you have this parametric model, it never sees the nuisance factors and it can never learn false correlations. And this formed the basis for feature selection algorithms in very classical machine learning. And one key thing to note here is that for nuisance factors that are not correlated with the target, no additional supervision is required. That is, we don't need annotations for these factors. Just because they're not correlated, we can remove them from the model. But when we think about biasing factors, they actually form a subset of the factors that are correlated with the target. And so there is no way to automatically infer whether a factor is biasing or truly essential for predicting the target. And in these cases, additional supervision is required for removing the bias. And if we consider this setup, then we can again split the set of factors into two groups, F1, which is the desired information that we want to use for predicting the target, and F2, which is the undesired information that we want to exclude from the prediction task. So Now we'll talk about our framework, given this setup. So our approach is to achieve invariance in neural networks by learning a split representation of data into E1 and E2. So this is going back to the same idea of splitting the factors into two subsets, F1 and F2. So E1 is supposed to capture essential and desired information for predicting Y, and E2 is expected to capture undesired information about X, such as nuisance and bias, which should not be used for predicting the target. And invariance to uncorrelated nuisance is achieved through a new competitive learning scheme, whereas invariance to correlated bias is achieved through additional penalty if the biasing factors are encoded in the E1 embedding. So let me first talk about the framework components. There is an encoder which learns this split representation of data. There is a predictor which tries to predict Y from E1. There is a noisy transformer, psi, which converts E1 to its noisy version E1 tilde. A decoder which tries to reconstruct X from the noisy version of E1 along with E2. And the key thing to note here is that E1 is noisy, E1 tilde is noisy, and it is unreliable for X reconstruction. With this in mind, let's look at how we achieve invariance to uncorrelated nuisance. The key idea here is to achieve nuisance through information discovery and separation. Information is discovered through the Y prediction and X decoding goals, and separation is brought about due to the combination of disentanglement between E1 and E2. Remember, we want to learn a split representation of data, so we have to enforce disentanglement between E1 and E2. They should be independent representations. And also, because the psi E1, sorry for the mistake here, but the psi E1 is noisy and it cannot be relied upon for reconstruction. So what ends up happening is that we get this competitive scenario where the predictor tries to pull everything about Y into E1, but the decoder tries to pull everything about X into E2, because the psi E1 or E1 tilde is unreliable, and and better reconstruction can be achieved by pulling everything into E2. But the problem is that there can be no information overlap between E1 and E2. So every factor of data has one choice: either go into E1 and help the prediction task, or go into E2 and help with perfect reconstruction. And the overall objective of this training can be seen as a weighted loss function, where there's a component for Y prediction, there is a component for X reconstruction, and there is a penalty for disentanglement. So we want E1 and E2 to be disentangled. Digging deeper, we can consider two asymptotic cases for alpha and beta in this setup. First, if alpha is very big compared to beta, this model reduces to a feed-forward network, which is just encoding data and predicting Y from it. It's as if there is no reconstruction objective, because the weight given to the reconstruction objective is just so small. On the other extreme, we have the case where beta is very big and alpha is very small, and this reduces to an autoencoder. So you have the X going to E2, going to the decoding task. And it is as if the prediction task does not exist. Now, if we transition from the first case to the second case, that is, we have a very high alpha and a very low beta, and we start to slowly increase beta, we see that the nuisance factors that are uncorrelated with the target will now start to migrate to the E2 embedding, because they cannot contribute anything to the prediction target anyway, but they can improve the reconstruction by being more readily available instead of being available through a noisy version of E1. And we can see that if we keep increasing this beta, there is more and more say given to the reconstruction task, and more factors will be encoded in E2 versus E1. So we reach this optimal point eta star, beyond which factors that are truly relevant for the prediction task will also start migrating to E2, because the reconstruction is so dominating now. Sorry.
And the way to determine these hyperparameters would be, say, like evaluation, like cross-validation.
Yeah. So you can do cross-validation, and the systematic way to do it is that you fix alpha to a high value and beta to a low value, and you can just keep increasing beta and train more models until you see that eta star, after which the performance drops. So you don't have to try all possible combinations.
But because it looks like so the real factor is eta, which is the relative ratio of alpha and beta.
Right.
So really you only have one hyperparameter to tune, right?
So beta is the hyperparameter to tune if you just keep alpha fixed at a high value. And you also want to play with gamma so that, it depends on the data. And sometimes a higher gamma might be required for disentanglement versus lower gamma for other tasks.
Right. And I'm trying to remember what was gamma again?
So gamma is the loss weight for the disentanglement term. Yeah. So if you keep gamma fixed to a reasonably decent high value, and you just have to tune the beta. That is it. So now that we have seen how invariance is achieved to uncorrelated nuisance, let's talk about invariance to correlated bias. So again, gender and race, for example, are biasing factors, and sometimes they are correlated with the target, but these are false correlations. We do not want to use them in the prediction task. So the way to achieve invariance to them is to penalize the model if E1 encodes anything about the biasing Z. And for this case, we have to know what the biasing Z is. So for example, we need gender or race annotations in the training data to get rid of these factors in the prediction process. So if we add that to the previous objective, now the objective has this additional term which penalizes the model if E1 encodes this biasing correlated Z. And again, so going back to the previous comment, now we have one more hyperparameter, but really you have to just play with beta and delta in this case. Okay, now that I have described this very abstract, nice framework, let's see how do we even implement this. So we start by going back to the general framework. So we have the setup, we have the encoder, decoder, the predictor, and we have this noisy transformer. We want disentanglement, but there are some missing pieces here. For example, what is a good noisy transformation? How do you achieve noisy transform? So in our implementation, we use dropout, which is nothing but multiplicative independent Bernoulli noise. It could be some other parametric noise model, which can be trained using data, but we did not play with that. Now, the two remaining questions are, how do we disentangle E1 and E2? And how do we eliminate the biasing Z from E1? And we do this in an adversarial way. So first, looking at disentanglement as an adversarial task. So disentanglement is commonly viewed in terms of mutual information. So if the mutual information between two variables is 0, they are disentangled. But we can also think of it in a prediction format. So if you have two variables A and B, they are disentangled if you cannot predict one from the other, or vice versa, right? So if you cannot predict B from A or A from B, then they have no mutual information, they are disentangled. And we use this setup to come up with an adversarial game. Now we have two more modules to our framework, two disentanglers. So this one tries to predict E2 from E1, and this two tries to predict E1 from E2. And this is only possible if E1 and E2 contain overlapping information. Otherwise, you cannot predict one from the other. So you can see that the goal of this one and this two are in direct opposition of what we want. We want disentanglement, but this one and this two are trying to predict one from the other, which is they are trying to see if the embeddings are not disentangled. So we can play a minimax game over here. Second is bias elimination as an adversarial task. So using the same setup as the disentanglement, we see that if you can predict bias from the E1 embedding, then it is biased. So we now want to fool a discriminator and say that the encoding does not contain bias. And this can only be achieved if the embedding does not truly contain the biasing factor. So we have this new adversarial discriminator dis-Z, which tries to predict Z from E1, and its goal is in direct opposition to the desired invariance to this biasing Z. And the complete adversarial model looks like this. So you again have the encoder, which has the two embeddings E1 and E2. You're trying to predict Y from E1. And you have this noisy transformer as dropout, which gives you the E1 tilde, which is concatenated with E2 and used for reconstructing X. The two adversaries, dis1 and dis2, try to predict one embedding from the other. And the DZ discriminator tries to predict the biasing Z from the E1 embedding. And we can see that this gives us a setup for an adversarial game between two composite models. The one in blue, which we call the main components, and the ones in orange, which are the adversarial components. And the training, how we do training is basically alternating between training the blue components versus the orange components. And we use a schedule, like we train M1 every K times we train M2. And in our experiments, we played with both K equals 5 and 10. We found that to work reasonably well. In an ideal case, you would want to train M2 to convergence before any update to M1 so that you can get the best gradients, but that does not scale. So we have to stick with a scheduled scheme. Okay, so now that we have put everything together, let's talk about numbers.
What's the schedule? Sorry, last line. The alternate training. What is what you're doing? I understand the M1 and 2, 1 to K.
Right. So when we are training this model with through backpropagation, when we sample mini batches from data, we first sample a mini batch, freeze everything, freeze all the weights in M2, update M1. Now in the next K mini batches, we freeze M1 and we update M2. And we keep freezing and unfreezing in an alternating fashion, 1:K times.
Well, in the result of so I don't know why it's not 1-to-1, what the K or what the impact of K is.
Yes. So ideally speaking, you would want to train the M2 components, that is the discriminator and the disentanglers, to convergence. So that will give you the best estimate, right? So you would want to train the disentangler to convergence. So now you truly know whether E1 can be predicted from E2 or E2 can be predicted from E1. Or for the Z discriminator, you would truly know whether Z can be predicted from E1. And then you would freeze the M2 and update M1 by one step of gradient descent. But that becomes infeasible because now you don't know how long you have to train the M2 components before you can update M1.
Okay. So there's always to define.
Okay, we can discuss this after. Okay, thank you. Okay, let's see how this model performs. First we evaluated the model on the extended Yale-B dataset. It is a dataset for face recognition, and it contains images of people's faces with different lighting conditions. And the prediction target is the subject ID, which is 38 classes. And the nuisance factor is the lighting condition, which is binned into 5 classes. That is the direction of lighting, whether it's coming from the 4 corners or up front. And the key thing to note here is that when we are training our model, we do not use the nuisance information because we consider this to be an uncorrelated nuisance. So it should not be required, but all the previous models do use it. All the previous state-of-the-art models do use it. And we see that even without using this information, we are able to beat the state-of-the-art by a large margin. We get not only a very high accuracy of predicting the subject ID from E1, but also an accuracy of predicting the nuisance factor from the latent embedding closer to random chance. So here random chance is 0.2 and we get 0.24, which is pretty close to random chance. And again, we have not used any nuisance annotation for training this.
So lighting condition nuisance factor was like starting, it wasn't continuous variable, right?
No, it was binned into 4 corners and frontal, so 5 classes.
5 classes. And they were represented as discrete.
Yes, yeah.
One more question. Why is it that you have the maximum mean discrepancy a dash on bias?
Yeah, so that is a number we quoted. And unfortunately, that is a very old model. And in their paper, they were using a measure of invariance, which is now considered not appropriate. Like they were using logistic regression for estimating the Z accuracy. But now what is followed is we train a 2-layer or a 3-layer neural network to convergence after we have trained the model to predict the nuisance from the E1 embedding. So I don't, yeah.
In other words, if you'd have to train the model yourself and do all that work, which of course would probably take a lot of time.
Yeah, so all of the numbers except for CVIB and our model are quoted directly from their papers.
Actually, which paper is that?
Which one?
So the other numbers come from a different paper, one paper?
No,
Okay.
all other different papers.
So if you Google the names of those methods, you'll find the papers.
Yes, yeah.
On the nuisance, you said that you didn't use the nuisance factor for Unify, but the architecture before you're using the nuisance factor, is that the earlier simple architecture, or what do you use for this experiment?
So I'm sorry if I missed this, but
so you're using the first architecture, not this one.
So this is the general framework, and we previously mentioned that for removing uncorrelated nuisance, we do not need this DZ discriminator. So we train without the DZ discriminator for Yale-B. Yeah, so we are not using any Z annotation. So if you don't look at DZ, nothing in the model uses Z information, like Z annotations.
You include that block.
Yeah. So as I was saying, we beat the previous methods on both metrics, and we can also look at how the embedding looks like. So the raw data is actually naturally clustered by the lighting direction. You can clearly, even in 2D, you can clearly pinpoint the lighting condition of any image. And when we look at E1, that is the embedding that is used for predicting the subject ID, we see that there is no lighting information. Every single cluster is a subject ID. The colors might be repeated, but the subject ID is the number that is on the cluster. And when we look at E2, the other embedding, which is supposed to contain everything else about the data, is actually clustered by the lighting condition. So we see this natural separation of information.
What do you mean it's clustered by the lighting?
The columns are the same.
Yeah.
Lower left, I see. Yeah. Lower right, I see. Yeah.
So it's already or on the left, cluster on the left, cluster on the right.
Those represent
so it will capture this common nuisance.
Right.
For the most part. And the places that are like outliers or misclassifications, do you know why they're
it might be that two lighting conditions, some images are at the border of two lighting conditions. So
this embedding doesn't represent the distance, it's supposed to capture, like those green dots, for example, on the bottom, they're really far away from the other green dots.
Yeah, so those might be closer to the blue. I think that is.
So it's something as raw data. When you embed the nuisance reduction on the raw data, you have two green dots in the blue, and those are kind of propagated to E2, which is kind of feature. This is like a bug actually, and the triangles, with triangles on the dots are also here.
I see. So that's like kind of embedding or kind of T-SNE type groups.
Yeah, these are all T-SNE embedding. So that is T-SNE of the first one is the T-SNE of the raw data. So you see natural clustering by the lighting condition and not by the subject ID. And you see the same thing in E2.
So this seems a very easy task. I work with data sets where there's no such good separation of clusters,
Of the nuisance factor.
Of the nuisance factor.
Right.
Okay, so would your method work if there's high overlap in those?
We have more experiments, but we expect it to. And we have been playing with more complicated data sets even after this work. Sorry.
One question to better understand your method. Essentially, your training is, your prediction is based on E1, and an E2 being essentially like an autoencoder is useful for visualization purposes.
No.
Like it does dimensional reduction, but I didn't see how that was useful for prediction.
Right. So let's step back a little bit.
Yeah.
So if we look at this general framework,
Yeah.
Both E2 and a noisy version of E1 are used for reconstruction. And E1 is used for predicting Y, And this noisy transformation and the enforced disentanglement cause this competition condition. So, and because of this competition, these features of data separate into E1 and E2.
Yeah.
So E2 can be thought of like a trash bin to contain
So you,
all of the.
never use it for prediction.
We never use it for prediction.
I see,
So for prediction, you would only go from X to E1 to Y.
Yes.
Once you have trained the model, you don't need anything else.
I see.
That is all you need.
Okay.
Okay. So yeah. So we see that the E1 embedding does not capture the lighting information, as was also reflected by the number of accuracy of predicting the lighting information from E1. And when we try to reconstruct the faces from these two embeddings, so we train decoding models post hoc. That is, we have already trained the full framework. We just take the embeddings and train decoding modules on top of them from scratch. And we see that clearly the original data, so every block is for one subject. And in every block, I first show the original image and the reconstruction from E1, followed by the reconstruction from E2. So you can see that the reconstruction from E1 almost never contains the lighting information, especially the direction of the light, whereas E2 contains that information but does not contain anything about the subject identity. So E1 reconstructions from E1 look like mean faces with only the subject information and no lighting information, whereas reconstructions from E2 look like mean faces of lighting condition with no subject information. Okay, so moving on, I have results on another data set. It's a data set of chairs. So it contains chairs, 1393 different types of chairs, which are rendered at various yaw angles in full 360 view. I believe there are about 30 different angles, and they are binned into 4 classes. That is whether they're facing forward, backward, left, or right. And this information is again not used for training our model, but it was used for training the other models. And we see that we beat the previous models on both accuracy of predicting Y and that of predicting Z. Here the random chance is 0.25 for predicting the angle class from the E1 embedding, and we get 0.34, which is decently close. And when we try to visualize this, we see this this phenomenon. So the raw data is almost clustered by the angle class. That is where the chair is facing. So here the separation is not as good as Yale-B, but you can still see that there is clustering by the angle class. When we look at the E1 embedding, we see that it does not contain, for the most part, it does not contain any such information about the yaw angle. But when we look at E2, it is clustered by the angle. And again, we see that there is this natural separation of information without needing to use labels for the angle. When we reconstruct from both E1 and E2, we see that that the E1, when we try to reconstruct from E1, there is no angle information. So you see this mean of a 360 view of the chair, which only contains some information about the class of the chair. Whereas when we reconstruct from E2, for the most part, it does not contain information about the class of the chair, but it contains information about where the chair is facing.
Why is this task more difficult than the faces task?
So that's the Yale-B data set is very clean, and it's like in a very controlled setting, and the lighting conditions are very easily separable. Whereas here, a lot of chairs are confusing, and some chairs might be better discriminable from certain angles versus not. So there is more difficulty here compared to.
I almost would expect this method to learn some. What's that, Elizabeth? I forget, like in the fundamental classes. What's the in physics? There's the. I'm just ground.
Primitive classes.
There's a word for that. Someone kind of like, there's like ground, not classes. They're no. There's what are we speaking to this? Like, so like a chair has 4 legs, right? This is what we think about when we think about 4 chairs. So would expect this kind of become you want to capture this.
Yeah. So actually, that kind of information is captured. So these reconstruction examples can be somewhat confusing because they are trained after the model is already trained. So you will also see, for example, if you are training a decoder to reconstruct an image with different variations of a certain factor as the target, but the input does not contain that feature, it will try to do a mean of that. So because E1 does not contain any angle information, so that's why you see that this 360.
So this was the neural networks like CNN kind of.
Yes. Yes.
I mean, is there any way you can try? Is there any neural network technique you can use to represent these kind of translations or rotations? I mean, a CNN would just be invariant to position in the image, but
yes,
it's not going to kind of rotate the image. Is there any way to encode that maybe in the?
So
because then it would make we would reconstruct them really well. You would basically be able to from any image to get the full first front-facing version of the chair. I don't know if it's possible.
Right. So if you do not train it in this fashion with the invariance framework, if you just train a feed-forward network for predicting the chair type, it will capture the angle information as well. And when you try to reconstruct from that, you won't see 2 different reconstructions. You will see just one reconstruction which has both chair type and the pose of the chair in the embedding. But here we are trying to split the representation into 2 groups, where one is invariant to the nuisance factors, and here the nuisance factor is the rotation angle. So in one reconstruction, you see the rotation angle, and the other you don't. Okay, so moving to the next data set, we took the MNIST data set of digits, and we rotated it at different angles. So plus and minus 22.5 and plus and minus 45. The prediction target is still the digit class, but here now we have nuisance factors, the rotation angle, and we have grouped them into 3 classes, whether they are not rotated, or they are rotated left, or they are rotated right. But this information is not used for training the model once again. And we provide numbers for different theta. So we train the model on the big theta over here, that is 0, 20.5, and 45. But we also tested on plus minus 55 and plus minus 65. So these are out of domain cases. And we can see that in all cases, we get a significant boost from previous year of the art. And that is especially big in the case of out of domain cases. So this goes back to my previous comment that if you train a model to exclude a certain kind of information in the prediction process, you expect it to be more robust to it, because the model never encodes the rotation class in the E1 embedding. It never uses it for the prediction. Whether you give it a rotation at an angle that it previously saw or not, that ideally should not matter, and you would see a more invariant prediction. And also the accuracy of
I guess it has not fully captured that rotation, no? Because you still get a pretty big hit if you rotate the digit.
Oh yeah.
Quite a bit.
Yeah. So ideally speaking, if you could, ideally speaking, you would want this to be completely separate, but after a certain angle, it is not possible to discriminate.
Training was something with 22 and 45 degrees.
Yes.
And you're testing beyond that range.
Yes. So if you go like too far, then it is impossible to determine what this digit is. Like for
9s and 6s.
Yeah. And also for the accuracy of predicting the class, you can see that it is almost exactly random chance, 0.33. And once again, when we try to visualize the data, the raw data is clustered by the rotation angle very naturally, whereas the E1 embedding is clustered by the digit class. This might not look impressive, but this might. So when we train a feed-forward neural network without any invariance framework, versus when we train it with the invariance, we see different behavior when we try to visualize out of domain cases. So we trained both the vanilla feed-forward network and the invariance framework on angles from 0 to 45, both positive and negative. But then we visualized for plus and minus 55. And you can see that in the case where we do not train it with the invariance framework, in the embedding space, you can see that each digit cluster is split into multiple clusters corresponding to different rotation angles. And that is more obvious when you look at the bottom row for both cases. You can see that you can actually pretty well classify, even in 2D, you can classify whether the digit is rotated left or right. Whereas when you train it with invariance, you cannot. Even when you go like beyond the domain on which you train the model. And when you try to reconstruct, you see the same thing. So the image is rotated left or right, but when you try to reconstruct from E1, you see the digit class, but you don't see any rotation information. You see a mean of the rotation. And for E2, it does not capture any digit information, but it captures these weird features which most likely also contain the rotation information. And the key idea is that for MNIST, there are many nuisance factors. So unlike Yale-B or chairs, where we ourselves control the nuisance factor, that is the angle or the lighting condition, here there is more free range of different nuisance factors. The digit stroke, how thick it is, elements of handwriting style, tilt. There are a lot of factors, and somehow all of those get clubbed into the E2 embedding. Next, we move to a fairness case. So here we're talking about the adult data set. It's a toy data set, but it's still used in all the previous works for assessing how biased your model is, even after you use invariance. So it's a data set of income, and the target is to predict whether a person's savings is more than or equal to 50,000, and the biasing factor is age. And here, because it is biased, we have to use it for training. There is natural correlation between age and the prediction target in the training data. So here we use the full model that I previously showed. And we see that we are able to match the state of the art on predicting the savings while being invariant to age. Here, the majority class of age has 65 is 0.65 of the entire data set. So that is what you expect if the model is invariant.
And being able to, of course, match the that's definitely great. The question I have then is it faster than the other method?
Not exactly, but I have more results. Sorry.
So the biasing factor here is, again, it's age, but it's continuous, like in the integer?
It is club. So here, here it is binned into young and old, and there is a threshold for that.
I see, and you said that 2/3 of the people are old.
Yeah. So if the model is truly invariant, you expect 0.67 to be the accuracy of predicting Z.
But if you bend it into more classes, like the actual
right
10, 17, 25, whatever.
Yeah.
What do you expect performance to?
I would still expect the performance to be pretty good, and it might. I've never tried it, but it might be even better because now we have more fine-grained annotation, and we might be maybe not for this data set because we can already achieve invariance, but I guess we have to evaluate it on those fine-grained classes to figure out that the model can still discriminate between those fine-grained classes or not. And then if we train with those fine-grained classes, we expect that the model will become invariant to even those fine-grained classification of age.
And my expectation is the reason why I have this just 2 bits is simply because you want to compare with previous papers.
Yes, yeah. So that we can do the benchmark.
How many example sizes does it?
That is I think this one has more, around 10,000, I think, if I'm not wrong.
Are you able to decompose the bias from age into bias against older people versus bias against younger people? Because only one of those are protected.
Yeah, so let me see if I got it right. So do you mean like calculating the accuracy for the majority class versus the minority class?
Right, so if you're using this for credit scoring, you can't age discriminate against people over 40, but under 40, it's fine.
I don't know how fine that is. Like if you truly want invariance, you wouldn't use age as a factor at all. Does that?
No, the goal is to make the most money by booking loans.
But so the goal there is to maximize the profit, but here the goal is to achieve complete invariance. Yeah. So I don't know how questionable it will be if you do the selective discrimination versus not, but maybe, I mean, if you don't do any of this, like you can always maximize profit, but you will make unfair assessments and
ungeneralizable assessments. They may not actually maximize profits.
Right.
That's not your point.
Sure. Yeah.
Anyway.
If you were to do a more fine-grained analysis of age groups, could you penalize different age groups differently?
You could. So in terms of training, that just amounts to putting some sample weights or class weights in the training process. And you could do that. Yeah. So there is nothing stopping this model from doing that. Oh yeah, and one more thing going back to your question was that it is not faster, but if you use the full model, you are achieving invariance to both correlated and uncorrelated undesired factors. Whereas in previous models, you only achieve invariance to the specific factor that you ask the model to be invariant to. So besides age, there might be some uncorrelated factors that are also in the data. And if you use the full model that I described, then the model will naturally become invariant to those as well.
So the hope is that improves generalizability. So the idea would be that in an additional data set, you'd achieve higher accuracy than the others. Right?
Yes.
That'd be cool. Okay.
Yeah. So if there was a way to measure other nuisance factors, like for this data set, I don't have enough domain knowledge to know what is a nuisance factor versus what is required for predicting Y. We could calculate this accuracy of Z for all of those, and we could see, whether it becomes invariant to those or not. And when we look at the embedding, we can see that the raw data is biased. Like there is a clear separation between the two age groups. And in the E1 embedding, we see that it becomes fair. So you don't see any separation between the two age groups. Whereas all that bias information migrates to E2. So E2 is again discriminable by the biasing class. Okay. So we also tested on the German data set, which is also used for benchmarking fair representation methods. And here the goal is to do credit assessment. And we want to predict whether the person has high or low credit. And the biasing factor is gender. So we have to use it because we have to use it for training because it is a biasing factor, correlated biasing factor. And we see that all of the previous models as well as our model gets perfect invariance on this for gender. But we have a significant boost on the prediction of the credit category from the E1 embedding compared to the other models.
Will you mean this perfect invariance? Because this is not 20%.
Yes, it's a 20/80 split between the two genders. And when we look at the embedding, we see that you can see a cluster for the minority group in the raw data. You can also see that in the E2 embedding, but you cannot see that in the E1 embedding.
Have you tried doing like a balance? If you take that set and you subset it and you create balance that set, like 50-50 male and female, and you train with that, would you get that 50-50 ratio?
Actually, that might still be problematic because there might be other features in the data set that might be correlated with age or gender. For example, education and other.
Yeah. I'm just curious to see if you get similar result.
We did not try that because, like in this method, we don't care if various factors in the feature space in the data space are correlated. Eventually, in the latent space, they should not be. There should not be any bias in the latent space. So this brings me to the end of my talk. To conclude, we have a unified invariance method for both nuisance and bias. And we do this by learning a split representation of data into desired and undesired factors. It requires no annotation for uncorrelated nuisance. And it can additionally use annotations of correlated bias to eliminate them. And in the adversarial instantiation of this framework that we showed results on, we achieved disentanglement and bias elimination through adversarial training. We achieve state-of-the-art performance on both prediction and invariance tasks. And it is a general framework that anyone can apply to any task. Like in the entire description, I did not mention any assumptions or any priors on the data. You can apply this to any problem really. And for resources, the unsupervised case for removing uncorrelated nuisance from the data for prediction is already published at last year NeurIPS. And the complete model that also does fairness is going to be submitted to a journal soon, and it will be on archive within a couple of weeks. So keep an eye out for that. And the code will also be on GitHub in a couple of weeks. Any questions?
It's a general framework, but how much data do you need to train it? Because neural networks generally require lots of data for parameters. So, what are the limits for the data requirements?
Right. So that is always a problem with neural networks. So here you would need a lot of data, but if you don't have a lot of data, you could use other forms of regularization that you already use in straightforward networks, like some L2 regularization, dropout, or batch normalization. Use a smaller model with fewer parameters, but like it is a neural network in the end, so it will require data. But the Yale-B dataset that uses only 190 samples for training.
Which one?
The Yale-B dataset that I showed the first time for face recognition with lighting condition, there are only 190 samples for training, but that is a very simple data.
But it's a face then.
Yeah.
But more like popular, right?
Right.
Tile stuff.
Yeah, I mean, right.
Predictions of 200 subjects, maybe like 50 observations from each.
And also
Right. Yeah, unfortunately, that is a problem with neural network. And this is a framework for invariance in neural networks. So can't really get around that. Any other questions?
So what's next?
Is
this a solved problem?
No, it's definitely not a solved problem. We have submitted another paper to ICML this year, and hopefully that will get in. That uses a different strategy for invariance. We are also looking into a more theoretical understanding of the split representation learning and what it entails. Like how can we more formally write it and analyze it and hopefully improve it. So there are a lot of venues to look into. And one, like, how can we also do this in a better way without using adversarial training? That is one direction that I want to look in, because like the most recent state of the art before our model was also using adversarial training, because they found that without adversarial training, it was difficult to actually remove bias from data. So one thing we are looking into is how do we do that?
Training just means supplying examples that are difficult?
No, I'm referring to the Z discriminator module that tries to predict Z from the E1 embedding and then penalizes the model if it can find Z in the E1 embedding.
And Z is
Z is the correlated bias.
Right,
Yeah.
right, but it's known kind of.
Yes, yes, yes. For correlated bias, you always need annotation because there is no other way to determine if a feature is biased versus should be used for classification. Right? Okay, thank you.